Aloha! In this 11th video of the Acids and Bases series, we discuss acid strength and molecular structure. We're not doing any calculations in this video, but we will talk about how to predict if acids are strong or weak, or if you have two acids, which one's stronger. So this video gives us a little insight into acid strength based on the molecular structure of the acid itself. Let's first discuss binary acids. These are when hydrogen is attached with one other element, like hydrochloric acid, HCl, or hydrofluoric acid, HF. Those are binary acids. For binary acids, acid strength depends on bond polarity and atomic radius. These two factors, if you know about them, you can predict the acid strength. Let's first discuss bond polarity. You remember polar bonds are when one of the atoms is more electronegative than the other one. So if you're thinking about bonds between hydrogen and other elements, the ones that are the most polar would be the most acidic. Now, the trend in electronegativities, if you remember, is like this. Here's the top right-hand corner of the periodic table, and electronegativity increases going across the right and going up. So the top right-hand corner is the most electronegative region of the periodic table. So electronegativity is when the element pulls electrons. So fluorine is the most electronegative element. It has the greatest ability to pull electrons towards itself. If you have hydrogen attached to various atoms across the periodic table, such as lithium, carbon, and fluorine, first, hydrogen attached to lithium, in this case hydrogen is more electronegative than lithium, it will pull the electrons towards itself. So hydrogen would have the electrons more than lithium would, and hydrogen will definitely not detach as a positive ion. It would detach as a negative ion, if anything. If hydrogen is attached to carbon, well, the electronegativities are similar for hydrogen and carbon, and this is not acidic. What we're looking for is for when the other atom is pulling the electrons away from hydrogen. And that's the case for fluorine. If hydrogen is attached to fluorine, fluorine is a very small electronegative element. It's really pulling the electrons towards itself. And it's like hydrogen doesn't really have any electrons, and it's almost detached as a proton already, so it's easy for it to detach as a positive proton. So bond polarity affects the acidity in such a way. So the more polar the bond, the easier hydrogen can detach. The other effect is atomic radius, and to see this trend, we can take a look at HF, HCl, and HBr. So these are three acids. Now, HF and HCl and HBr, the electronegativity actually decreases as you go down this column, but the acidity increases. So the atomic radius trend kind of goes opposite to the bond polarity trend, but atomic radius is a little bit more important than bond polarity in this case. If hydrogen is attached to fluorine, the fluorine is really small, and so hydrogen is right next to it. It's pretty well attracted to it. Chlorine is a much larger atom. Hydrogen is further away from the center of the chlorine. Therefore, the bond is weaker and easier for hydrogen plus to detach. HBr, the bromine atom is so large that hydrogen is way out here now, and it's very easy for hydrogen to detach. So acidity actually increases as you go down this column, even though bromine is a little less electronegative than chlorine and fluorine. So even though the electronegativity decreases a bit going down here, the atomic radius is very important. And so as the electronegativity increases and the atomic radius increases, these would be the most acidic right there. So hydrochloric, hydrobromic, and hydroiodic acids are the most acidic ones. So that's binary acids. Let's discuss briefly oxyacids. These have the formula HXON, so hydrogen, some element, and a certain number of oxygens, such as perchloric acid, HClO4, would be an example of an oxyacid. Now, for oxyacids of a particular element, like the oxyacids of chlorine, as I've written them here, the acid strength increases with the number of oxygens. So if you're considering the oxyacids of chlorine, HClO4, HClO3, HClO2, and HClO, the one with the most oxygens is the most acidic, and the one with the least oxygens is the least acidic. That's the trend. Now, it's pretty easy to see why that trend exists. The perchloric acid, if you draw its Lewis structure, you can see the hydrogen over here, and these four very electronegative oxygen atoms are really pulling the electrons that are bonded to the hydrogen towards this side of the molecule. So these four oxygens make it very easy for that hydrogen to detach without its electrons. And so there it is, and there's the anion that would form, the conjugate base anion perchlorate. Now, another way to view why this is a very strong acid is because the perchlorate anion, that negative charge is distributed all across this atom. Right now, it's kind of associated with that oxygen as shown in this resonance structure, but this anion can be drawn with 4 resonance structures. So I've only shown one, but you could have drawn the single bond going up here, and the negative charge would be associated with that one. It's, it could have gone over here, over there. The 4 resonance structures represent this ion, and the more resonance structures there are, the more stable that structure is. So the reason this would dissociate is because it's trying to form a stable anion. So it's easier for this anion to form since it has 4 resonance structures. For chloric acid, HClO3, this is a pretty strong weak acid. In fact, the Ka is on the order of 1. So about 50% of these molecules will dissociate. And some people even consider this a 7th strong acid. Chloric acid has this resonance structure. There's only 3 oxygen atoms here, so they're not pulling the electrons over towards this side as much as up there, but that's still 3 oxygens, and this hydrogen can detach pretty easily. And so, this would be the conjugate base anion that's formed, and this time there would only be 3 resonance structures. So it's, not as stable as that one up there. And the trend continues. HClO2 has an even smaller equilibrium constant, 2 oxygen atoms pulling the electrons over here, and the conjugate base anion only has 2 resonance structures. And then finally HClO, sorry, you couldn't quite see that, so it's even less stable, and then only 2 resonance structures. And then the last one is hypochlorous acid, HClO. This is the weakest. There's only 1 oxygen. The equilibrium constant is much less here. It's only 1 oxygen pulling the electrons, and the conjugate base anion only has 1 structure. So, pretty weak acid there. So for any set of oxyanions, that would be the trend. So we did it for chlorine, but you can consider the ones for bromine or nitrogen, and you would see a similar trend. So that concludes this video. In our next one and final one on the acid and base series, we'll discuss how to classify solutions. Stay tuned for that. Aloha.